Tonight, we're going to look at the actual distance to every planet in our own solar system. Most people assume that distance is a fixed number, something you could look up once and know for good. It isn't. It changes constantly, depending on where each planet sits in its orbit. And the real number involves far more than distance alone. It involves fuel, orbital velocity, radiation, and time. The real question isn't just how far a planet is. It's what that distance actually costs to cross, to survive, and to come back from. And once you factor all of that in, some of the planets you assumed were close turn out to be some of the hardest to reach in the entire solar system. And by the end of tonight, you're going to understand exactly why the distance to our neighboring planets is far worse than most people realize. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand what these distances actually mean, you need to know how astronomers measure them. The astronomical unit. 1 astronomical unit is the average distance between Earth and the Sun, about 93 million miles. It is the yardstick astronomers use because the actual mile figures become unmanageable quickly. Mercury sits at 0.39 astronomical units from the Sun. Venus at 0.72. Earth at 1. Mars at 1.5. The asteroid belt spans roughly 2 to 3.5. Jupiter at 5.2. Saturn at 9.5. Uranus at 19.2. Neptune, the outermost planet, at 30 times the Earth-Sun distance. About 2,790,000,000 miles. And that number barely registers because our brains were not built for this. Not for distances measured in billions of miles. So what we're going to do is make it real. We're going to put you in a spacecraft, give you the best propulsion we actually have, and make the journey. Before we can go anywhere, there are already 2 problems standing between you and every planet in this solar system. The first is the rocket equation. Konstantin Tsiolkovsky, a Russian mathematician working in the late 19th and early 20th century, published the mathematical relationship between propellant mass, exhaust velocity, and final speed in 1903. It is one of the most important equations in spaceflight, and also one of the most unforgiving things in physics. The equation says your spacecraft's final velocity depends on 2 things: how fast the propellant exits the engine, and the ratio of the spacecraft's initial mass, including all its fuel, to its final mass after the fuel is burned. What makes this equation brutal is that the relationship is logarithmic. To double your final speed, you do not double your fuel. You square the mass ratio. To triple your speed, you might need 1,000 times more propellant than for a single increment of speed. The math spirals against you exponentially. This is the reason a Saturn V rocket, standing 363 feet tall and weighing 6.5 million pounds fully fueled, could only send about 107,000 pounds toward the moon. It is the reason modern rockets are roughly 90% fuel by mass. The payload, the spacecraft, the crew, the life support, the instruments, is a small fraction of the total mass at launch. To travel faster, you need more fuel. More fuel means more mass to accelerate. More mass means more fuel to accelerate it. Every additional increment of speed in interplanetary space costs an exponentially increasing amount of propellant. The second problem is that everything in space is moving. Earth is orbiting the Sun at about 67,000 miles per hour. Every other planet is doing the same, each at its own speed. You cannot point a spacecraft at where a planet is and fly toward it, because by the time you arrive, the planet has moved. A Hohmann transfer is how you navigate both constraints at the same time, not by overcoming them, but by accepting them entirely. Instead of burning continuously toward a moving target you can never afford to chase, you launch into an elliptical orbit, an oval path that intersects your starting planet's orbit at one end and your destination planet's orbit at the other. You leave Earth, curve outward through space, and arrive at the far end of that ellipse precisely when the destination planet arrives at the same point. The timing has to be exact. The planet has to be in the right position when you launch, so that it meets you at the other end of the arc, months or years later. This is a Hohmann transfer, and it is the most fuel-efficient route between two planets. And given what the rocket equation demands, efficiency is not a preference. It is the only option. These distances are not just long, they are long in a way that the best available propulsion technology cannot shorten below years for most destinations and below decades for others. Let's talk about the Sun first, because it sets the scale for everything else. The Sun is 93 million miles from where you're sitting. Light leaves its surface and reaches your eyes in about 8 minutes and 20 seconds, which means when you look at the Sun, which you shouldn't, you are seeing it as it was 8 minutes ago. Not now, 8 minutes in the past. The Sun you see is already history by the time the photons reach you. The fastest spacecraft humanity has ever launched is the Parker Solar Probe, which hit about 430,000 miles per hour during its close passes to the Sun by falling toward it under gravity. Out in interplanetary space, under your own rocket propulsion, you are not going 430,000 miles per hour. A spacecraft launched from Earth on a standard trajectory using chemical propulsion travels between about 25,000 and 36,000 miles per hour, once it has left Earth's gravity well. At 30,000 miles per hour, reaching the Sun from Earth takes about 129 days, 4 months, of traveling toward a star that will vaporize your spacecraft if your thermal protection fails, even briefly. The Parker Solar Probe uses a carbon composite heat shield, about 4.5 inches thick, to endure surface temperatures approaching 2,300 degrees Fahrenheit on the sun-facing side. Without that shield, the spacecraft would not melt. It would vaporize. There would not be debris. There would be plasma. The Sun is not a destination. It is the reference point, the anchor of our solar system, the thing everything else is measured from. And even it is 4 months away at conventional spacecraft speeds, lethal under any scenario where the engineering fails. That is the baseline. Every planet in this story starts from there. Mercury sits at an average of about 36 million miles from the Sun, which sounds close. But planetary distances do not work by solar proximity alone. They work by the positions of both planets at the moment you launch, the orbital mechanics of the curved trajectory you must follow, and the fuel constraints of your spacecraft. Mercury's orbit is the most elliptical of any planet in the solar system. Its distance from the Sun ranges from about 28.5 million miles at its closest point to about 43.5 million miles at its farthest. Combined with Earth's own orbital motion, the Earth-Mercury distance swings dramatically. At closest approach, about 48 million miles. At farthest, about 138 million miles. Average over time, around 77 million miles. A Hohmann transfer orbit to Mercury takes roughly 3 to 5 months. But real missions to Mercury are far more complex. Messenger, the first spacecraft to orbit Mercury, launched in August 2004 and did not enter Mercury orbit until March 2011. 6.5 years. Not because the spacecraft was slow, because arriving at Mercury is genuinely difficult. Mercury orbits the Sun in 88 days. It moves fast, matching its orbit, and slowing down enough to be captured by its gravity requires shedding an enormous amount of velocity. The fuel-efficient way to do that is gravity assists, flying past other planets and using their gravity to reshape your trajectory and adjust your speed without burning propellant. Messenger flew past Earth once, Venus twice, and Mercury itself 3 times before achieving orbital insertion. 6.5 years of carefully choreographed planetary encounters to reach a planet that is 48 million miles away at its closest. Bepi Colombo, the joint European-Japanese Mercury mission that followed, launched in October 2018 and will not enter Mercury orbit until 2026. 7 years. Once there, the planet delivers a specific kind of brutality. The sunlit surface reaches about 800 degrees Fahrenheit. The night side plunges to about -290, a swing of over 1,000 degrees between hemispheres, with no atmosphere in between to moderate anything. Mercury's exosphere is not an atmosphere in any meaningful sense. It is a scattering of atoms sputtered off the surface by solar wind bombardment. It provides no insulation, no pressure, nothing breathable. Mercury's magnetic field is about 1% the strength of Earth's. Solar energetic particles stream across the surface, nearly unimpeded. Surface gravity is 38% of Earth's enough to feel, not enough to counteract the bone loss accumulated during months of transit. 3 months to 7 years to reach Mercury. Then you land on something that simultaneously bakes and freezes, with no atmosphere and near-continuous solar radiation exposure. That is the easy one. Venus sits at an average distance of about 106 million miles from Earth. Getting there takes 4 to 6 months on a Hohmann transfer orbit. Venus is often called Earth's twin. Similar size, similar mass, similar bulk composition. In the early 20th century, before any spacecraft reached it, Venus was the subject of genuine scientific speculation about possible life, perhaps tropical oceans under the cloud layer, perhaps vegetation. The clouds covering it completely prevented optical observation of the surface. What lay beneath could only be inferred. The inferences were hopeful. They were wrong. The surface pressure on Venus is 92 atmospheres, equivalent to being about 3,000 feet underwater in Earth's oceans. The atmospheric composition is 96.5% carbon dioxide, which has driven a fully realized runaway greenhouse effect. Surface temperatures average about 865 degrees Fahrenheit. Globally, not the daytime high. The average temperature across the entire planet, dayside and nightside, everywhere. Hotter than Mercury at its maximum sunlit temperature, despite Venus being almost twice as far from the Sun. This is what a greenhouse effect looks like when it has run its full course with no corrective mechanism. The cloud layers are concentrated sulfuric acid, ranging from about 75 to 96% acid by mass in the densest layers. The Soviet Venera program sent 12 landers to Venus over roughly 2 decades. Each was engineered specifically for the environment. Titanium pressure vessels, phase change cooling systems, pre-cooled before entry, rapid descent profiles to minimize time in the acid clouds. Every single one was destroyed by surface conditions within about 2 hours. The longest survivor was Venera 13, which lasted 127 minutes before succumbing. It sent back color images of the Venusian surface during that time. Orange basaltic slabs, a dim, filtered sky. 127 minutes of science, then silence. For a human crew, landing on Venus is not a question of difficulty. It is simply not possible with current technology. 92 atmospheres of pressure requires structural engineering we cannot build at human habitable scale. 865 degrees of ambient temperature requires thermal management. No current life support system can sustain indefinitely. Concentrated sulfuric acid attacks most materials over time. None of these problems is solvable in isolation with what we have today. Together, they are not solvable at all. Venus is 4 to 6 months away, and when you arrive, the surface is closed. Now, Mars. Mars receives more sustained public and political attention as a human destination than any other planet. Multiple space agencies, multiple corporations, multiple national governments have stated intentions for crewed Mars missions within the next 2 decades. The number most commonly used is 7 months to Mars. That is roughly correct for a one-way Hohmann transfer orbit at a favorable launch window. 7 months. During those 7 months, the following happens to your body, whether you want it to or not. Your skeleton loses 1 to 2% of bone mineral density per month in the load-bearing bones, spine, hips, pelvis, femurs. 7 months means 7 to 14% of bone mass gone before you land. You are arriving at a planet with 38% of Earth's surface gravity on a skeleton already compromised by the journey to get there. Your muscles atrophy despite 2 hours of mandatory daily exercise. Your cardiovascular system remodels to function without gravity. Your intracranial pressure rises from fluid redistribution, pressing against the optic nerves, potentially altering your vision in ways that may not fully reverse after return. Your total radiation exposure during transit is approximately 375 millisieverts. NASA's career radiation limits for astronauts set at a 1% excess lifetime cancer. Mortality risk fall between 600 and 1200 millisieverts, depending on the individual. One 7-month transit to Mars consumes well over half of a career radiation budget in a single one-way transit. The round trip, including surface operations, brings total exposure to roughly 600 to 900 millisieverts. One mission. Most or all of a career limit. Then there are solar particle events. Major solar eruptions can deliver radiation doses capable of causing acute radiation sickness within hours. The largest recorded events would have been potentially lethal to crew members in interplanetary space without adequate shielding. Mission designs include a storm shelter, a compartment in the spacecraft with extra radiation shielding. You get warning, minutes to hours, maybe. You retreat to the shelter. Whether the shielding is adequate for that specific event depends on the event. You manage the risk. You do not eliminate it. When you arrive at Mars, the signal delay to Earth ranges between 4 and 24 minutes one way. Round-trip communication, 8 to 48 minutes. In an emergency, you report your situation and wait. At closest orbital approach, you wait 8 minutes for Earth to receive your transmission and 8 more minutes for any response. At maximum distance, nearly 50 minutes total. Whatever outcome results from the emergency has already played out before any advice arrives. And then, orbital mechanics trap you. Earth and Mars orbit the Sun at different speeds. The window for a fuel-efficient return transfer opens once every 26 months. You arrive after 7 months. You wait on the surface for 14 to 18 months as the planets reposition. You depart in 7 months. Total round trip, 2.5 to 3 years. For the nearest planet. That is what the distance to Mars is when you unfold the number into an actual itinerary. The surface of Mars itself is no refuge. The atmosphere is about 1% as dense as Earth's at sea level, almost entirely carbon dioxide. It provides no breathable oxygen and no meaningful thermal insulation. Surface temperatures swing between about -195 degrees Fahrenheit at the poles in winter and about 70 degrees Fahrenheit at the equator in summer. The average surface temperature across the planet is about -80 degrees Fahrenheit. You cannot stand on the surface without a pressure suit. You cannot breathe without life support. The thin atmosphere does not block ultraviolet radiation effectively. Mars has a very weak, patchy, magnetic field, remnants of an ancient global field that collapsed roughly 3 to 4 billion years ago. Without that field, solar wind strips the upper atmosphere over time and delivers radiation to the surface with minimal magnetospheric protection. NASA's Perseverance rover has demonstrated in situ resource utilization on Mars. The MOXIE experiment successfully converted carbon dioxide from the Martian atmosphere into oxygen. Small amounts. Proof of concept, not production. Scaling MOXIE-style oxygen production to support a human crew would require equipment orders of magnitude larger than anything we have landed on Mars so far. Making propellant for a return journey from local Martian resources, a concept called in situ resource utilization for propulsion is technically feasible in principle and is a major piece of current mission architecture planning. But as of now, it has not been demonstrated at mission-relevant scale. The surface of Mars is the most hospitable destination in the outer solar system for human life, and it is a place where any system's failure becomes life-threatening within minutes. No rescue is coming. The nearest possibility of help is at least 4 minutes away by the fastest signal we know how to send, and that signal cannot do anything except carry words. This is the planet closest to Earth, in its most favorable orbital position. Beyond Mars sits the asteroid belt, extending from about 2.2 to 3.2 astronomical units from the Sun. Not the dense gauntlet of science fiction, not a wall of spinning boulders that spacecraft must dodge through. A vast, sparse distribution of rocky and metallic bodies, spread across a volume so enormous that the average distance between any two notable objects is hundreds of thousands of miles. The total mass of everything in the asteroid belt is estimated at less than 4% of Earth's moon. If you swept it all together, you would not have a planet. You would have something smaller than the moon. Spacecraft pass through it routinely, on autopilot, without incident. The belt is not the hazard. The belt is a transition. What lies on the other side of it is where the scale of distances shifts upward in a way that changes the nature of every mission fundamentally. Jupiter sits at an average Earth distance of around 391 million miles. A Hohmann transfer orbit takes approximately 2 years and 9 months. Nearly 3 years. One way. All of the biological consequences of the Mars transit, the bone loss, the muscle atrophy, the radiation accumulation, the cardiovascular remodeling, the intracranial pressure continue for nearly 3 years instead of 7 months, and then compound. Radiation exposure on the journey outward to Jupiter, through the same interplanetary environment as the Mars transit, accumulates over nearly 3 times as long. The crew lives in a spacecraft for 3 years before they reach their destination. The communication delay to Jupiter is between about 32 and 52 minutes one way. Round trip, between about 1 hour 4 minutes and 1 hour 44 minutes. Mission control cannot support the crew in real time. They cannot monitor a reading, notice an anomaly, and call the crew within seconds the way they can for the International Space Station. The crew makes every significant decision without waiting for Earth's input, because by the time Earth's input arrives, the situation has already changed. Jupiter itself has no solid surface. It is primarily hydrogen and helium, compressed by gravity through states of matter not found naturally on Earth. The transition from gas to liquid is gradual. Deeper still, under enormous pressure, hydrogen becomes a metallic fluid that conducts electricity. Upper atmospheric winds reach about 340 miles per hour. The Great Red Spot, a storm system, observed continuously, since at least the mid-17th century, spans about 10,000 miles across. It has been shrinking gradually over recorded observation. It was roughly 40,000 miles across in the 19th century. It is now about 10,000. Still larger than Earth. Still there. Jupiter's magnetic field is 20,000 times stronger than Earth's. Within that field, the radiation belts near Jupiter and its inner moons create one of the most intense natural radiation environments in the solar system. Jupiter's magnetosphere extends outward millions of miles in the direction away from the Sun. It would be visible from Earth as a structure larger than the full moon in the sky if human eyes could see magnetic fields. Europa's surface receives a radiation dose of about 5,400 millisieverts per day. That is not an annual figure. That is per day. Unshielded humans on Europa's surface would be incapacitated by radiation sickness within hours. The dose that causes the first symptoms of acute radiation syndrome is about 1,000 millisieverts. Europa's surface delivers that in about 4 to 5 hours. And yet, Europa is one of the most compelling destinations for life detection in the entire solar system. Beneath its radiation-baked surface ice, a shell estimated at about 6 to 19 miles thick, there is a global subsurface liquid water ocean. Its total volume is estimated to be about twice that of all Earth's oceans combined. The ocean has existed for billions of years, kept liquid by tidal heating as Jupiter's gravity flexes Europa's interior. Hydrothermal activity on the ocean floor is plausible, possibly confirmed. If life exists anywhere else in the solar system, Europa is one of the few places where the conditions for it are genuinely present. But getting to that ocean requires landing on a surface that is delivering 5,400 millisieverts per day, drilling through at minimum 6 miles of ice under conditions unlike anything previously attempted in space exploration. and deploying instruments into a liquid ocean on another world. None of those individual problems is trivial. Together, they are among the hardest engineering challenges in planetary science. Europa Clipper, launched in October 2024, arrives at Jupiter in 2030. 6 years of transit. It will study Europa from orbit, executing about 50 close flybys over the course of its mission. It carries 9 scientific instruments, including a radar that can probe beneath the ice shell. From orbit, not from the surface. What it learns will determine whether any future lander mission is ever seriously proposed, funded, and built, which itself would require another transit of roughly 6 years after decisions made in the late 2030s at the earliest. 3 years to reach Jupiter. An hour-plus communication gap for every exchange. Radiation that ends unshielded humans in hours around the most scientifically interesting moons. No solid surface. A subsurface ocean sealed beneath miles of ice that no current technology can reach. The Galilean moons of Jupiter deserve more than a passing mention, because they collectively represent one of the most diverse and scientifically rich environments in the solar system. Jupiter has 4 large moons, discovered by Galileo Galilei in January 1610. The first objects observed to orbit something other than Earth or the Sun, the discovery that helped overturn the geocentric model of the cosmos. Those 4 moons are Io, Europa, Ganymede, and Callisto. They are very different from each other, despite orbiting the same planet. Io is the most volcanically active body in the solar system. More volcanically active than Earth. More active than anything else we have found anywhere. Jupiter's gravity, combined with the gravitational tugs of Europa and Ganymede, flexes Io's interior through tidal forces, continuously and powerfully. That flexing generates heat, enormous amounts of heat, which drives continuous volcanic eruption across the surface. Io has hundreds of active volcanoes. Some erupt continuously. Some erupt in massive outbursts that deposit material across enormous areas of the surface within hours. Io's surface has essentially no impact craters. The volcanic resurfacing erases them faster than they can accumulate. The entire surface is being remade, continuously, by internal heat that Jupiter's gravity provides for free. Io sits about 262,000 miles from Jupiter, which places it deep within Jupiter's radiation belts. The radiation environment at Io is extreme. Any spacecraft visiting Io closely receives intense radiation exposure with every pass. Any human presence at Io, even in orbit, is not currently feasible without shielding far beyond what we have built for crewed spacecraft. Io is extraordinary. Io is also, for human visitors, essentially untouchable with current technology. Europa sits just outside Io's orbital radius, at about 417,000 miles from Jupiter. We have discussed Europa's subsurface ocean in detail. But there is something worth adding about the surface. Europa's ice shell is geologically young. The surface is relatively free of large impact craters compared to other icy moons, suggesting the surface is being continuously renewed either through subsurface ocean material welling up or through tectonic-like activity in the ice shell itself. The surface is marked by long linear ridges and fractures called lineae, some running for thousands of miles, and by disrupted regions where the ice surface appears to have broken apart and refrozen in chaotic patterns called chaos terrain. These features suggest that the ice shell is not static. Material from the ocean may have reached the surface. Material from the surface and from the radiation environment above it may have worked its way down into the ocean. This potential exchange between the surface and the ocean is one of the most important things Europa Clipper will investigate. If oxidants produced at the surface by radiation can reach the ocean, they could support chemical energy sources for life, even in the absence of sunlight. This is the same chemistry that drives life around Earth's hydrothermal vents, not photosynthesis, but chemosynthesis. Energy from chemistry, not from light. Ganymede is the largest moon in the solar system, larger than Mercury. It is the only moon known to have its own internally generated magnetic field, a dipolar field, similar in structure to Earth's, produced by convection in a liquid iron core. Ganymede also likely has a subsurface ocean of liquid water, sandwiched between layers of ice. ESA's JUICE mission, the Jupiter Icy Moons Explorer, launched in April 2023 and will reach Jupiter in 2031. Its primary target is Ganymede, where it will eventually enter orbit, the first spacecraft ever to orbit a moon other than Earth's. Callisto, the outermost of the 4 Galilean moons, orbits outside the main radiation belts at about 1,170,000 miles from Jupiter. It is heavily cratered, one of the most heavily cratered surfaces in the solar system. It shows little evidence of internal geological activity. But it too may have a subsurface ocean, suggested by its response to Jupiter's magnetic field during Galileo spacecraft flybys. Callisto's position outside the worst of Jupiter's radiation belts makes it the most accessible of the 4 large moons for human missions in the long term, if human missions to Jupiter ever materialize. It would serve as a potential base for human operations in the Jovian system, with lower radiation exposure than any of the inner moons. 4 moons, each a world in its own right, each raising profound scientific questions. Each accessible only after a nearly 3-year transit, followed by operation in one of the most radiation-intense environments in the solar system. That is what waits on the other side of the Jupiter transit. Not a single destination. A system of worlds. Saturn sits at an average Earth distance of around 746 million miles. A home and transfer orbit takes approximately 6 years. 6 years of interplanetary transit. Every biological consequence of the earlier journeys continues, but stretched across 6 years. Radiation accumulating across the entire transit. 6 years of bone density changes. 6 years of cardiovascular remodeling. 6 years of living in an enclosed spacecraft with a small crew, far from Earth, far from everything. The communication delay to Saturn from Earth is between 67 and 92 minutes one way. Round trip, over 2 hours at closest, over 3 hours at farthest. Cassini launched in October 1997. It flew past Venus twice, Earth once, and Jupiter once. Gravity assists, accumulated over years, to build speed on the long journey outward. It arrived at Saturn in July 2004. 6.5 years of travel. For 13 years afterward, Cassini orbited Saturn and its moons, returning extraordinary science about a system that had never been seen up close for more than hours. Every command sent to Cassini took between 67 and 83 minutes to arrive. Every data packet returned took the same time to reach Earth. The operations team planned every maneuver in advance. They sent commands into the future and received records of the past. They managed a spacecraft they could never interact with in real time, over a mission spanning more than a decade. In September 2017, Cassini was flown deliberately into Saturn's atmosphere. Running low on fuel, with the mission nearing its end, the decision was made to destroy it rather than risk an accidental collision with Titan or Enceladus moons that might harbor life and that could not be risked for contamination. The final transmission from Cassini arrived at Earth 1 hour and 23 minutes after Cassini had already ceased to exist. The science team knew the moment was coming. They knew the delay. They watched the final signal arrive from a spacecraft that had been gone for over an hour. Saturn's ring system spans about 175,000 miles, edge to edge. The rings are in most regions about 30 feet thick. A structure covering that span and 30 feet deep, made primarily of water ice. It is one of the most striking structures in the solar system, and it is almost certainly temporary on geological timescales. Material is raining into Saturn's atmosphere along magnetic field lines. The rings could be gone within about 100 million years. Enceladus sits about 148,000 miles from Saturn's center. It is small, about 313 miles across, and it is one of the most remarkable objects in the solar system. Geysers erupt from near its south pole, venting water vapor, ice particles, and complex molecules into space at speeds high enough to escape Enceladus's gravity and supply Saturn's E-ring. Cassini flew through those plumes multiple times. It detected molecular hydrogen, carbon dioxide, methane, organic molecules, silica nanoparticles, indicating hydrothermal reactions between water and rock at high temperature. The chemistry is consistent with what you find around Earth's deep-sea hydrothermal vents, the environments where life does not merely survive, but thrives, deep below any sunlight, fueled entirely by chemical energy from the rock. Enceladus has a confirmed global liquid water ocean beneath its surface. It has active geysers we can fly through and sample without landing. It has chemistry, matching the conditions that support life on Earth. It is arguably the most accessible place in the outer solar system to search for biosignatures. And it is 6 years away, with a 2.5-hour communication round trip, and no dedicated follow-on lander or sampler mission on any near-term approved schedule. A proposal called Enceladus Orbilander has been studied in detail, a mission that would orbit Enceladus and eventually land on its surface, sampling the plume material directly. It is not currently funded. It has not been approved. It exists in the category of missions that scientists want, have designed, and cannot yet get funding to build. Titan, Saturn's largest moon, bigger than the planet. Mercury has a dense nitrogen atmosphere with a surface pressure 1.5 times Earth's at sea level. Lakes, rivers, and rain of liquid methane, dune fields of hydrocarbon particles. A world with a complete hydrological cycle running not on water but on methane. Complex organic chemistry happening at about -290 degrees Fahrenheit. Dragonfly, a rotorcraft mission developed by NASA, is planned to launch in the late 2020s and would arrive at Titan around 2034, nearly a decade from now. A helicopter on another world, flying through Titan's thick atmosphere, relocating to sample different sites, studying the organic chemistry of a moon that some astrobiologists consider a plausible environment for exotic life. Life operating on entirely different chemistry than anything on Earth. 6 years of transit to fly a helicopter in another world's sky. The engineering is extraordinary. The timeline reflects the distances. There is something worth understanding about how we know what we know about these worlds. Most of what we have described in this section, Enceladus's ocean, Titan's methane lakes, Europa's subsurface ocean, the detailed storm structures of Jupiter, Neptune's wind speeds, was learned from a small number of spacecraft, many of them flying past on single trajectories or spending limited time in orbit. Cassini was the exception. 13 years in orbit around Saturn gave scientists a dataset they are still analyzing. Papers are still being published from Cassini data. The mission formally ended in 2017. Researchers are still finding things in the archive. That is what a long-duration orbiter mission does. It does not give you one pass, one set of images, one window of opportunity. It gives you seasons. It gives you years of watching a system evolve in real time. A single flyby gives you hours. An orbiter gives you years. The difference in scientific return is immense. And the reason we do not have orbiters around every interesting destination is the reason we have been discussing since the beginning: the distances and the time and money it takes to cross them. Uranus is where the solar system stops feeling local. Average distance from Earth, roughly 1,600,000,000 miles. A Hohmann transfer orbit, 9 to 10 years. Voyager 2 launched in August 1977. It reached Uranus in January 1986. 9 years and 5 months. The encounter lasted hours. A few days at closest approach, a brief window of close observation, and then Voyager 2 continued outward toward Neptune. Since that pass, since those hours, in January of 1986, no spacecraft has returned to Uranus. No orbiter. No atmospheric probe. No lander. One visit. One encounter. In all of human history. That is the sum total of our direct, close-up study of the seventh planet. Hours of data, nearly 40 years ago, from a spacecraft moving through on its way somewhere else. The signal delay to Uranus from Earth is between 145 and 170 minutes one way. Round trip. Between 4 hours, 50 minutes, and 5 hours, 40 minutes. Nearly 6 hours for a single exchange. You send a command in the morning. It arrives at the spacecraft nearly 3 hours later. You receive confirmation of execution nearly 3 hours after that. 6 hours of temporal displacement for every single interaction. Not because the technology is slow, because the distance is real. The Uranus orbiter and probe was designated the top new large mission priority in the National Academy's 2022 Planetary Science Decadal Survey, the document that guides NASA's planetary science investments for an entire decade. The decision came after careful comparison with other compelling destinations: Neptune, Enceladus, Venus, the Moon. Uranus won the comparison on a combination of scientific return, technical readiness, cost, and the rarity of favorable launch windows. The earliest realistic launch window for a Uranus mission is the late 2030s. Transit time from that window, about 13 years. Around 2050. That is about 25 years from now. A child born today will be a young adult before the first dedicated Uranus orbiter arrives. The questions the mission would address have been sitting unanswered since January of 1986. Uranus's axial tilt is 97.8 degrees. It rolls around the Sun, essentially on its side. Every other planet rotates roughly upright relative to its orbital plane. Uranus is tipped almost completely over. Each pole spends 42 years in continuous sunlight, then 42 years in total darkness. The most extreme seasonal variation in the solar system. The tilt was almost certainly caused by a massive collision in the early solar system, something large enough to knock the entire planet over. And it has stayed sideways for billions of years. The magnetic field of Uranus is as strange as its tilt. It is misaligned with the rotation axis by 60 degrees and offset from the planet's geometric center. Instead of a roughly dipolar field aligned with the poles, like Earth's, Uranus has a wobbling, asymmetric magnetic field that changes character dramatically as the planet rotates. No other planet in the solar system has a magnetosphere like it. And we don't fully understand why. Uranus radiates almost no internal heat outward. Every other giant planet, Jupiter, Saturn, Neptune, radiates more heat than it receives from the Sun, evidence that their interiors are still cooling from formation. Uranus appears to be an exception. Either it is not generating significant internal heat, or it is trapping that heat through some layered atmospheric structure that prevents it from reaching the surface. Both options are scientifically significant and poorly understood. The result of that missing heat, the coldest atmospheric temperatures of any planet in the solar system, about -371 degrees Fahrenheit in the upper atmosphere. Colder than Neptune, despite Neptune being 50% farther from the Sun. Neptune has a clear, residual internal heat source. Uranus, for reasons still not established, apparently does not or cannot release it. That asymmetry between two otherwise similar ice giant planets is one of the major open questions in planetary science. Uranus also has a system of narrow, dark rings, discovered in 1977, and at least 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope. Several of those moons may have subsurface oceans of their own. Miranda, one of the inner moons, has a canyon system, Verona Rupes, with cliffs dropping as far as 12 miles. We know this from a handful of images taken during the Voyager 2 flyby. That is everything we have. Everything we know about Uranus's moons, its rings, its magnetic field, its weather. Its interior, essentially, all of it comes from a few days of encounter data collected in 1986. The next opportunity to answer the questions that data raised, approximately 2050. Neptune is the last planet. Average distance from Earth, roughly 2,400,000,000 to 2,900,000,000 miles, depending on where both planets sit in their orbits. A Hohmann transfer orbit, approximately 12 years. Voyager 2 launched in August 1977. It reached Neptune in August 1989. 12 years. It is still the only spacecraft ever to have visited Neptune. Not one orbiter. Not one atmospheric probe. Not one lander. One flyby. 12 years of travel. A handful of days in range. And then Voyager 2 crossed Neptune's orbit and continued outward into interstellar space, which it eventually reached in 2018, 41 years after launch. The signal delay from Neptune to Earth sits between 234 and 266 minutes one way. Round trip, between 7 hours 50 minutes and 8 hours 52 minutes. Nearly 9 hours for a single exchange. You send a message in the morning. You receive a reply by late afternoon. One exchange. one back and forth. 9 hours. For a crew operating at Neptune's distance, Earth is not a support structure. Earth is a delayed correspondent, a voice from another world, answering questions that were asked half a day ago. Every significant decision is made autonomously by the crew. Everything time-sensitive is handled locally. Earth receives reports. Earth sends advice that arrives into situations that have already evolved, resolved, or worsened, with no ability to intervene in any of it. The August 1989 flyby revealed a dynamic, complex world. Upper atmospheric winds measured at around 1,200 miles per hour. The fastest planetary winds measured anywhere in the solar system, on the planet farthest from the Sun, where solar energy is at its weakest. Neptune's internal heat source, still releasing energy from formation, drives those winds. In the southern hemisphere during the flyby, there was a dark storm system, roughly the size of Earth, named the Great Dark Spot. By the time the Hubble Space Telescope observed Neptune in 1994, the Great Dark Spot had gone, disappeared. A storm, the physical size of our entire planet, present during 12 days of flyby observation in August of 1989, vanished before 1994. We have a few days of close-up data on it. We watched from Earth as it came and went. We have no record of when it formed, how it evolved, or exactly when it ended. Neptune's atmosphere is dynamic in ways we have barely documented. Triton, Neptune's largest moon, is one of the most unusual objects in the solar system. It orbits Neptune in the retrograde direction opposite to Neptune's rotation, and opposite to the direction every other large moon in the solar system orbits its planet. This is the clear signature of a captured object. Triton did not form around Neptune. It formed elsewhere in the outer solar system, almost certainly in the Kuiper Belt, and was gravitationally captured by Neptune billions of years ago. The capture process would have been violent. A body moving in the wrong direction, suddenly being held by Neptune's gravity, its original orbit rapidly transformed by tidal forces into the circular retrograde orbit we see today. That process generates enormous heat. It may have kept Triton's interior molten for hundreds of millions of years after capture. Triton's orbit has been slowly circularizing over billions of years through tidal interaction with Neptune. But tidal forces are simultaneously slowing Triton's orbital speed, causing it to gradually spiral inward. In about 3.6 billion years, Triton will cross Neptune's Roche, limit the threshold where tidal forces exceed the gravitational cohesion holding the Moon together. It will disintegrate. Neptune will then have a spectacular ring system built from the wreckage of its captured companion. For now, Triton is geologically active. Nitrogen geysers erupt from near the South Pole, driven by the very faint solar heating of nitrogen ice beneath a thin, transparent surface crust. The sunlight that reaches Triton nearly 30 astronomical units from the Sun is barely 0.09% of what reaches Earth. That fraction of solar energy heats nitrogen ice slightly. The warmed nitrogen sublimates beneath the transparent crust. Pressure builds. Eventually, it vents as a geyser, rising several miles into the thin atmosphere before being blown downwind. Active geysers. At negative 390 degrees Fahrenheit. At the outer edge of the solar system. Physics doesn't care about the temperature. It does what it does. we observed those geysers once. From a spacecraft that spent 12 years getting there. No funded return mission exists for Neptune. No approved follow-on mission is in active development. The scientific community has expressed strong desire for a Neptune Odyssey concept, a flagship orbiter and probe mission. It is not funded. It is not scheduled. It exists as a scientific aspiration against a backdrop of finite budgets and other compelling destinations. Neptune and Triton represent perhaps the most scientifically significant unvisited region in the solar system in terms of the ratio of what we know to what we suspect is there. And the barrier to reaching it is 12 years of travel and a 9-hour communication gap at the end. Now, step back. Every distance we've covered is a one-way measurement at some average orbital position. But orbits are ellipses. Both planets are always moving. The moment you commit to a trajectory, the distance is changing beneath you. Mars can be 34 million miles from Earth or 250 million miles from Earth, depending on where both planets are in their orbits. Jupiter ranges between 365 million and 600 million miles. Saturn, between 746 million and 946 million. Timing is everything. A mission launched at the wrong orbital configuration does not just take slightly longer. It may require a fundamentally different trajectory, significantly more propellant, or may simply not be feasible with the available launch vehicle. The windows close. For Mars, the launch window recurs every 26 months. For the outer planets, optimal windows depend on planetary alignments that recur on timescales of years to decades. The Voyager, 2 Grand Tour, Jupiter, Saturn, Uranus, Neptune, on a single trajectory, relied on a planetary alignment that occurs once every 176 years. That window was open in 1977. The project recognized it, secured funding, built the spacecraft, and launched by the deadline the universe set. The next comparable alignment for a similar grand tour is in the 2100s. The planets do not wait for institutional readiness. The window is there, or it is not. And when it closes, no amount of engineering or budget can substitute for the geometry. The communication delay deserves to be understood clearly because it is not just an operational inconvenience. It changes the fundamental relationship between a crew and the civilization that sent them. On the International Space Station, mission controllers monitor systems in real time. A sensor reading looks unusual. Within seconds, a flight controller notices, assesses, and calls the crew. The ISS is never more than a fraction of a second from Earth in terms of communication. Every significant system malfunction is a conversation between the crew and a ground team that can see the same data at essentially the same moment. Earth is present. Earth is engaged. Earth is a partner in every decision. On a Mars transit at maximum distance, round-trip communication time is 48 minutes. One exchange, 48 minutes. You report an anomaly. Earth receives the report 24 minutes later. Earth's assessment and recommendation depart immediately. It arrives 24 minutes after that. 48 minutes after you first describe the situation, you receive Earth's response to a situation that is now 48 minutes older. And beyond Mars, the delay only grows. At Jupiter, over an hour each way. At Saturn, between 2 and 3 hours round trip. At Uranus, nearly 6 hours. At Neptune, nearly 9 hours. The crew does not call home. The crew sends messages into the future and receives answers from the past. Earth becomes somewhere the crew is from, not somewhere they are. The mission becomes the world. The ship becomes the community. The crew becomes the autonomous decision-making authority for everything that matters, because no faster authority exists at those distances. This is not a failure of communication technology. This is the geometry of distance, acting on the speed of light. The speed of light is 186,282 miles per second. That does not improve with better technology. The signal delay to Neptune is over 4 hours each way, because Neptune is over 4 light hours from Earth. No antenna, no laser, no quantum entanglement changes the speed at which information travels through space. Distance divided by the speed of light. That is the delay. It is the delay forever, for any mission at those distances, for any conceivable future technology. The physics of it cannot be engineered around. It can only be accepted, planned for, and accommodated in every aspect of how missions are designed and how crews are trained. A crew headed to Neptune is not going on a long expedition where home is always within reach. They are departing for a place where Earth is a 9-hour delay in each direction, where the crew's own judgment, experience, and in-situ assessment is the only real-time intelligence available, where a medical situation, an equipment failure, or an unexpected scientific discovery is processed by the crew and acted on by the crew, with Earth receiving a report and sending thoughts that arrive when the situation has already advanced. The psychological design of deep space missions is as important as the engineering design. Crew selection for long duration, isolation, and autonomy is not about finding people who can tolerate confinement. It is about finding people who can function as a self-sufficient, decision-making community, at the edge of everything humans have built, with a 9-hour lag before the next voice from home. Let's go deeper on the radiation problem, because it is the most underappreciated obstacle in human spaceflight beyond Earth orbit. Radiation in space comes from 2 main sources. The first is galactic cosmic rays, high-energy particles that originate from supernovae and other energetic events throughout the galaxy. They travel at close to the speed of light. They penetrate most shielding materials. They are present everywhere in space, all the time, in all directions. The second source is the Sun itself, solar energetic particles, which are accelerated by solar flares and coronal mass ejections and can arrive at a spacecraft within minutes to hours of a solar event. These are more variable and more locally intense than galactic cosmic rays. On Earth, both are blocked by the combination of the atmosphere and the magnetic field. The atmosphere alone provides shielding equivalent to a column of water about 33 feet thick. The magnetic field deflects charged particles away from lower latitudes. At sea level, you receive about 2.4 millisieverts of natural background radiation per year. In low Earth orbit, the magnetic field still provides some protection, though the atmosphere does not. International Space Station crew members receive about 100 millisieverts per 6-month mission, 40 times the sea level annual dose. In interplanetary space, both the magnetic field and the atmosphere are gone. There is nothing between the crew and the full flux of galactic cosmic rays, plus any solar particle events. During solar minimum, when the Sun is quietest, galactic cosmic ray flux is actually highest, because the solar wind that normally deflects some of them is reduced. During solar maximum, when the Sun is most active and solar particle events are most frequent, Galactic cosmic ray flux is somewhat lower, but the risk of acute solar particle events goes up. There is no period in the solar cycle when both risks are minimized simultaneously. The galactic cosmic ray component cannot be blocked with any practical amount of conventional shielding. High-energy particles interact with thick shielding materials and produce secondary radiation, a shower of secondary particles that in some cases is worse than the original incoming radiation. Water, hydrogen-rich plastics, and polyethylene are better shielding materials than aluminum or steel because hydrogen is effective at absorbing the energy of incoming particles without producing as many secondary particles. Mission architecture proposals for Mars transit include water walls, lining the crew habitat with water-filled panels that serve double duty as radiation shielding and water storage. The reduction in dose is real, but not transformative. Water walls cannot bring interplanetary radiation doses down to Earth-equivalent levels. They can reduce the dose somewhat. They can provide better protection during solar particle events if the crew retreats to the most shielded compartment. But the galactic cosmic ray background accumulates regardless, and no passive shielding currently conceived will reduce it below levels that represent a meaningful health risk over a multi-year mission. Active magnetic shielding, generating an artificial magnetic field around the spacecraft to deflect charged particles the way Earth's field deflects them from the surface, has been proposed and studied. The required field strengths and the power demands make it technically challenging. No active magnetic shield has flown on a crewed spacecraft. The concept is not abandoned, but it is also not solved. The practical consequence of all of this is that every human mission beyond low Earth orbit carries a radiation risk that cannot be fully managed with current technology. For Mars, the numbers are survivable high, but within career limits if the mission is single and the crew does not return for multiple long-duration missions. For Jupiter and beyond, the radiation environment during transit, combined with the environments at destination, begins to approach levels where mission design must fundamentally grapple with the biological limits of what humans can endure. This is not a reason to stop. It is a constraint that mission architects work within and that motivates ongoing research into both better shielding and better medical countermeasures. But it is part of the true cost of the distances. Every mile of transit through interplanetary space adds radiation to the cumulative load. Every additional year of transit adds more. The outer solar system is not just far in the sense that it takes time to reach. It is far in the sense that the radiation environment between here and there extracts a biological price that has no analog in any prior human experience. One of the most striking facts about outer solar system exploration is how infrequently we return. Uranus, one flyby, January 1986. Neptune, one flyby, August 1989. Not one orbiter between them. Not one atmospheric probe that was dedicated to either world. Not one lander, one flyby each. Over 35 years ago. Why haven't we returned? The answer is not disinterest. The planetary science community has wanted to return to both worlds for decades. The answer is cost and time, and the way those two factors interact with the institutional structures that fund space exploration. A flagship planetary science mission, in the class of Cassini or the Galileo Jupiter orbiter, costs roughly $3 to $4 billion in total. That is a substantial commitment. But what makes outer planet missions uniquely difficult to sustain is not the price alone. It is the duration. Mission development takes about a decade before launch. Transit to the outer solar system takes 9 to 12 years. Science operations then run for years after arrival. Total investment from first serious proposal to final published data, 30 to 40 years. Sustaining political will, institutional commitment, and consistent funding across 3 to 4 decades of changing administrations, changing science priorities, shifting budget pressures, and evolving personnel is genuinely hard. The people who propose outer planet missions rarely live to see the final science published. The people who build the spacecraft often retire before it arrives. Graduate students who joined a project at its beginning become professors and then senior figures in the field before the mission completes. A Cassini-scale mission is not a project. It is a multi-generational enterprise. And it competes directly with every other scientific priority in the field. Science budgets are finite. Every dollar committed to a Uranus orbiter is a dollar not available for a Venus atmospheric mission, or the next Mars rover, or a next-generation space telescope, or an Enceladus sampler, or a lunar initiative. The Planetary Science Decadal Survey process exists precisely to make these trade-offs systematically. Once per decade, the national academies convene the planetary science community to assess priorities. What are the biggest open questions? Which missions would answer them? Which missions are technically ready? Which are cost-effective at their proposed science return? The resulting report sets NASA's direction for the following decade. When the 2022 Decadal Survey named the Uranus orbiter and probe as the top new large mission priority, it was the result of a years-long community process comparing Uranus to Neptune, to Enceladus, to Venus. Uranus won. Not because the others are unimportant, because the comparative analysis favored it on a combination of factors. Neptune will wait for the next decadal cycle, or the one after. Enceladus will get smaller, Discovery or New Frontiers class missions in the meantime, if any are approved. Venus has its own ongoing mission development in the form of Da Vinci and Envision, and the distances enforce every one of these choices with brutal finality. A failed outer solar system mission, a spacecraft that malfunctions during its 11-year transit and cannot be repaired from Earth, represents an entire scientific generation lost. You do not commission a replacement in the next budget cycle and send it next year. You wait for the next mission to be proposed, reviewed, funded, approved, built, which takes a decade, and then to travel another 11 or 12 years. The people who were mid-career when the failure occurred are near retirement when the replacement arrives. The graduate students working on the mission may not be in science anymore. The institutional knowledge has dispersed. There are no second attempts within a scientific lifetime for missions to the outer solar system. One of the reasons the decadal survey process takes years and involves hundreds of scientists is precisely this. The cost of making the wrong choice at those distances is not a setback. It is a generation of lost science. The decisions carry weight proportional to the distances. There are newer propulsion technologies being studied and developed that could change the transit time equation. Not the communication delay that is fixed by the speed of light and cannot be changed, but the years it takes to physically cross the distances. Nuclear thermal propulsion uses a nuclear reactor to heat propellant, typically liquid hydrogen, to extremely high temperatures, then expels it through a nozzle. The key figure is specific impulse, the measure of how efficiently a rocket uses its propellant. Chemical rockets, burning liquid hydrogen and liquid oxygen, achieve specific impulses around 450 seconds. Nuclear thermal engines can achieve 800 to 900 seconds, roughly twice as efficient. That efficiency translates directly to mission performance. A nuclear thermal rocket could cut a Mars transit from 7 months to approximately 3 to 4 months. It could cut a Jupiter transit from nearly 3 years to perhaps 12 to 18 months. Those are meaningful improvements, real improvements. The United States ran an extensive nuclear thermal rocket program in the 1960s, called NERVA Nuclear Engine for Rocket Vehicle Application. 23 engines were tested. The technology worked. The program was not shut down because the engines failed. It was shut down in 1973 for budgetary and political reasons as the Apollo program wound down and NASA's budget contracted. The engines were never flown in space. The technical knowledge sat in archives for decades. Current efforts to revive and modernize nuclear thermal propulsion include the Draco program, the demonstration rocket for agile cislunar operations, a joint DARPA and NASA initiative aimed at demonstrating a nuclear thermal rocket in space. If development proceeds on schedule, a demonstration flight could occur in the late 2020s. Flight-proven nuclear thermal propulsion could be available for crewed missions in the mid-2030s. This would meaningfully change the Mars mission profile. It would bring the outer planets somewhat closer in time. Jupiter transit, potentially under 2 years. Saturn, perhaps 3.5 to 4 years instead of 6. Still years. Still a profound commitment of time and human physical endurance, but meaningfully shorter. Beyond nuclear thermal, fusion propulsion remains a longer-term possibility. Fusion reactions, fusing light atomic nuclei to release energy, produce exhaust velocities potentially 10 to 20 times higher than chemical rockets. If that exhaust velocity can be channeled into thrust efficiently, transit times to the outer planets would drop from years to months. Jupiter, in weeks rather than years. Neptune, in months rather than a decade. The National Ignition Facility achieved fusion ignition for the first time in December 2022, a genuine scientific milestone, the first time in laboratory conditions that a fusion reaction produced more energy than the lasers driving it. ITER, the International Fusion Reactor under construction in France, is designed to produce 10 times the fusion energy of its input. These are real milestones toward fusion energy. They are not fusion propulsion. A compact, reliable, high-specific impulse fusion drive that can operate for months or years in space is decades of engineering development beyond current fusion energy demonstration. The path from a laboratory fusion reaction to a spacecraft fusion engine is long, and the intermediate steps are not yet clear. Fusion propulsion may be achievable in the second half of this century. It may not be achievable on that timeline. Both answers are consistent with current knowledge. Antimatter propulsion sits at the far end of the theoretical spectrum. Matter, antimatter. Annihilation converts mass to energy. At 100% efficiency, the most energy-dense reaction physically possible. In principle, antimatter propulsion could cut transit times dramatically. In practice, global anti-hydrogen production at facilities like CERN amounts to tens of atoms per second. The quantity needed for a propulsion system is many orders of magnitude greater than that. Antimatter propulsion is not a technology for this generation. It is an idea with correct physics and no practical path to realization in the near term. The realistic near-term improvement is nuclear thermal propulsion, available perhaps within a decade, offering roughly double the efficiency of chemical rockets and meaningfully shorter transit times to the inner and middle solar system. The realistic medium-term possibility is fusion propulsion, potentially available mid-century if development proceeds, offering dramatically shorter transit times across the entire solar system. The communication delay is not affected by any of it. Neptune will be 9 hours round trip, regardless of how fast you get there. The signal travels at the speed of light. Physics takes its toll, whether the journey takes 12 years or 12 months. There is a specific asymmetry in human knowledge that is easy to miss when you think about planetary exploration. We have mapped more of Mars than we have mapped of Earth's ocean floor. Let that sit for a moment. The floor of Earth's oceans, 2.5 miles below the surface, on average. In some places, nearly 7 miles down, is less completely characterized than the surface of a planet 140 million miles away. Mars has been photographed from orbit in extraordinary detail. The Mars Reconnaissance Orbiter's high-rise camera can resolve features on Mars's surface to about 10 inches, a resolution that would let it image a piece of luggage from orbit. Global topographic maps of Mars, derived from the Mars Orbiter Laser Altimeter, show elevation differences across the planet to accuracy of meters. We know the geology of Mars in some regions, better than we know the geology of parts of Earth's deep ocean. This is not a failure of oceanography. It reflects a straightforward physical reality. Space is easier to look through than water. You can orbit a planet and photograph its surface with relatively simple optics. You cannot shine light through 3 miles of ocean and photograph the floor. Acoustic mapping sonar provides coverage, but at lower resolution than optical imaging from orbit. The cost and difficulty of deploying sonar survey equipment across the entire ocean floor is significant. Mars has had dozens of orbiting spacecraft. The deep ocean floor has had far fewer mapping missions. The point of this asymmetry is not to argue about priorities. It is to illustrate how the tools available for exploration shape what gets explored. We go where we can see. We map what we can reach with instruments. And space, as hostile and remote as it is, turns out to be transparent in ways that the deep ocean is not, which is part of why we know as much as we do about Mars, despite the distance. And it is part of why the surfaces of Europa, Titan, and Enceladus, which can also be photographed from orbit across billions of miles, are characterized in some respects as well as the deep floors of Earth's own oceans. The distances are enormous. The physics of imaging through the vacuum of space is in some ways more forgiving than the physics of imaging through 3 miles of salt water. We know what we can see. And from orbit, across the solar system, we can see a great deal. What we cannot do is touch it, cannot sample it, cannot drill into it, cannot deploy instruments that require physical presence. For that, you have to go. And going costs what the distances charge. Beyond the planets, the solar system does not end. The Kuiper Belt extends from about 30 astronomical units, Neptune's orbit, to perhaps 50 astronomical units from the Sun. It contains hundreds of thousands of objects, larger than about 60 miles across, and many more smaller ones. Pluto is the most famous Kuiper Belt object. New Horizons flew past Pluto in July 2015, returning the first close-up images of a world at the edge of the classical solar system. What it found was not a dead, featureless rock. It found nitrogen glaciers actively flowing. It found mountain ranges of water ice rising 10,000 feet from the surface. It found a heart-shaped nitrogen ice plain, now informally named Tumbao Regio, large enough to span a significant fraction of the hemisphere facing away from Charon. It found a haze layer in Pluto's thin atmosphere, extended over 100 miles above the surface. It found evidence of ongoing geological activity on a world that, by size and distance from the Sun, had no obvious reason to be geologically active. Pluto surprised us. As every new destination in the outer solar system has surprised us, New Horizons then continued to a smaller Kuiper Belt object called Arrokoth, a contact binary, two lobes pressed gently together, which it flew past on January 1, 2019. Arrokoth is one of the most pristine objects ever observed directly. It formed in the early solar system and has changed very little since. It is, in some respects, a fossil from the formation of the planets, a remnant of the conditions that existed before the larger worlds swept up most of the available material. The Kuiper Belt is where some of the oldest unaltered material in the solar system resides. The Oort cloud, hypothesized to extend from roughly 2,000 to as far as 100,000 astronomical units from the Sun, is the source of long-period comets that occasionally fall inward toward the Sun. We have never directly visited any part of the Oort cloud. We have never sent a spacecraft beyond the Kuiper Belt, with instruments designed specifically for the interstellar medium. Though Voyager 1 and Voyager 2 have crossed into interstellar space, they were designed for the planetary encounters of the 1970s and 80s, not for extended interstellar study. An interstellar probe mission has been studied a concept for a spacecraft designed specifically to travel to the heliopause and beyond, with instruments tuned for the interstellar medium. To reach scientifically interesting distances around 1,000 astronomical units within a reasonable mission lifetime would require speeds around 20 astronomical units per year. Current spacecraft leave the solar system at about 3 to 4 astronomical units per year. Getting to 20 astronomical units per year requires propulsion technology we do not currently have. The distances beyond the planets are not just large. They are in a different category of large. They place destinations effectively outside the reach of any currently planned technology. The nearest star, Proxima Centauri, is about 4.24 light-years away. At Voyager 1's current speed, the journey would take about 73,000 years. That is the context in which planetary distances sit. Against the scale of the galaxy, our entire solar system, from the Sun to Neptune at 30 astronomical units, is a small bubble. The nearest star is not within the reach of any near-term or mid-term propulsion technology. But the planets are. Barely, and at enormous cost, and with timescales measured in years and decades. But they are within reach. That distinction between what is technically accessible and what is not matters. The planets are hard. They are not impossible. Everything beyond the solar system is, for now, in the impossible column. We are working at the edge of what is hard. One of the things the distances do that doesn't get discussed enough is what they reveal about the time it takes to learn anything. Consider how we learned about Mars. The first successful Mars flyby was Mariner 4 in July 1965. It returned 21 images, 21 grainy black and white photographs of a cratered, seemingly dead surface. The early picture of Mars was that it was a moon-like world, heavily cratered, geologically inert, probably lifeless. Mariner 6 and 7 followed in 1969, returning more images. The picture of a cratered, dead world appeared to be confirmed. Then, Mariner 9 arrived in November 1971 and entered orbit, the first spacecraft to orbit another planet. Mariner 9 arrived during a global dust storm that initially obscured the surface entirely. As the dust cleared, the spacecraft began photographing a world that bore almost no resemblance to what the earlier flybys had suggested. Olympus Mons, a shield volcano 3 times the height of Everest. Valles Marineris, a canyon system running roughly 2,500 miles across the equatorial region, roughly the width of the continental United States. Ancient river valleys. Flood channels that could only have been carved by water moving in enormous quantities. Evidence of a Mars that had once been warmer, wetter, and geologically far more active than the cratered terrain of the early flybys had indicated. The 21 images from Mariner 4 captured a small, unrepresentative sample of the surface and generated a picture of Mars that was fundamentally wrong. Not because the images were inaccurate, because 21 images are not enough. This is what happens when your only data comes from a brief encounter at enormous distance. You get a sample, possibly unrepresentative. You build a picture from that sample, and the picture is incomplete at best, misleading at worst, until more data arrives. The more distant the target, the longer the gap between samples. For Mars, the correction from the Mariner 4 picture to the Mariner 9 picture took 6 years. For Uranus and Neptune, the correction, if there is one, must wait until the next mission arrives. Uranus, around 2050. Neptune, unknown. Scientific understanding of distant planets is not a continuous accumulating process. It is a series of discrete events, separated by years or decades of no new close-up data. We have Voyager 2's 1986 Uranus data. We have Earth-based telescopic observations since then. We have no new close-up data. The picture we have of Uranus is fixed at the resolution and coverage of a flyby that lasted hours, nearly 40 years ago. The next revision to that picture is decades away. This is one of the most unusual features of outer solar system science. In almost every other field of scientific inquiry, data accumulates continuously. Experiments can be repeated. Measurements can be refined. New instruments can be deployed when old ones fail or become obsolete. Outer solar system, planetary science does not work that way. You get one mission per generation, if you're fortunate. You work with the data you have for as long as the next mission takes to plan, build, launch, and travel. The distances impose a specific temporal structure on knowledge itself. They determine not just how hard it is to go somewhere, but how often you can update your understanding of it. And for worlds at 10 or 12 years remove, the answer is rarely. Once per scientific generation, if the mission advocacy, funding, and political will align. That is a different relationship to knowledge than any other branch of science operates under. And it is entirely a consequence of the distances. The question of why we go, why we send spacecraft to places that take a decade to reach, at costs of billions of dollars, with communication gaps measured in hours, has a scientific answer and a different kind of answer. The scientific answer is straightforward. The outer solar system contains information about the formation and evolution of planetary systems that cannot be obtained any other way. The ice giants, Uranus and Neptune, are the most common type of planet found around other stars. More common than Jupiter-like gas giants. More common than rocky planets like Earth. We have 2 of them in our own solar system, and we have visited each of them once, briefly, decades ago. Understanding ice giants is not a parochial interest in our own backyard. It is necessary context for understanding the most common type of planet in the galaxy. The moons of the outer solar system, Titan, Europa, Enceladus, Ganymede, are not just scientifically interesting as individual objects. They are test cases for the habitability of worlds that orbit beyond the conventional habitable zone. The classical habitable zone around a star is the range of distances where liquid water can exist on a surface given appropriate atmospheric conditions. Earth sits comfortably within it. Mars is at the edge. Jupiter is far outside it. And yet Europa and Enceladus almost certainly have liquid water, not because they receive enough sunlight, but because tidal heating from the gravity of their host planets provides the necessary energy. This means the habitable zone is not just a ring around a star. It is potentially wherever tidal heating can maintain liquid water, regardless of stellar distance. In a galaxy with hundreds of billions of stars and an unknown but large number of planets with moons, the implication is significant. The number of potentially habitable environments in the universe may be vastly larger than the habitable zone calculation alone suggests. Studying the actual conditions within the tidally heated oceans of Europa and Enceladus is the only way to assess whether this theoretical habitability translates to actual conditions that could support life. That assessment requires being there, not observing from Earth, not modeling from first principles, being there, in orbit, with instruments in the plumes, eventually with landers on the surface. Being there costs the transit. Being there costs the years and the billions and the career commitments. But the question being asked, is there life beyond Earth, is among the most significant scientific questions humans have ever formulated. And the answers, if there are answers, are at the end of those distances. There is one more dimension to these distances that numbers and timelines don't fully capture. What it means to be the person who goes, or the person who stays behind and waits for signals that take hours to arrive. Human beings have a cognitive system built for social connection on timescales of seconds. You look at someone's face and read their expression in milliseconds. You hear a voice waver and register concern in a fraction of a second. The emotional bandwidth of human connection is essentially instantaneous, and it evolved over millions of years in environments where everyone you cared about was within earshot. Now consider what a 9-hour communication gap does to that system. Not just operationally, emotionally. A crew member at Neptune's distance sends a message home. It arrives 9 hours later. The family member on Earth responds immediately. That response arrives 9 hours after that. 18 hours pass between the message and its answer. In those 18 hours, the crew member has lived almost a full waking day. Events have happened. Moods have shifted. Context has changed. The reply that arrives is a response to someone who, in a meaningful sense, no longer exists in the same emotional state they were in when the original message was sent. Every exchange is a conversation between two people who are increasingly living in different temporal worlds. The crew member experiences time continuously at Neptune's distance. The family on Earth experiences time continuously near Earth. Their communications cross each other in transit, arriving out of phase with each situation they were sent into. Human beings manage this. Military deployments, submarines, distant expeditions, people have maintained meaningful relationships across communication gaps for as long as communication has existed. But 9 hours is different in character from delayed mail on an Antarctic expedition. The delay is a physical constant. It never gets better. It cannot get better. And the crew knows this not just as an intellectual fact, but as a lived daily reality. The structure of their emotional lives reshapes around it. Not in a catastrophic way, necessarily, but in a way that is unlike anything human beings have experienced before in the long history of exploration. Exploration by sea was dangerous. Exploration by land into unmapped territory was dangerous. But the explorers knew that if they made it back to port or back to a settlement, home was accessible. The journey was finite and physically reachable. At Neptune's distance, there is no accessible home. There is a 9-hour message gap and a 12-year return journey. The crew is not away from home. They are in a place that is not connected to home in any real-time sense. This is new, and the psychological design of missions that go there has to account for it, not just with communication protocols, but with crew selection, group dynamics, autonomy structures, and mental health support systems that work when Earth is a 9-hour delay away. The distance does not just affect how long it takes to get there. It affects who the crew becomes by the time they arrive, and what home means by the time they return. There is also something to be said about what the distances have already given us. Everything we know about the outer solar system, which is to say, most of the volume of our home planetary system, was learned in the last 50 years, almost entirely from a handful of spacecraft that were the product of extraordinary engineering and extraordinary patience. Pioneer 10 and Pioneer 11, Voyager 1 and Voyager 2, Galileo, orbiting Jupiter for 8 years. Cassini, orbiting Saturn for 13. New Horizons, flying past Pluto in 2015 and then continuing to Arrokoth in the Kuiper Belt. That is the full list of spacecraft that have reached the outer solar system. A small fleet, scattered over 50 years, launched across a distance that takes a decade to cross. Everything we know about Jupiter's interior, Saturn's ring dynamics, Titan's methane cycle, Enceladus's ocean, Europa's ice shell, Uranus's strange seasons, Neptune's winds, Triton's captured history, Pluto's nitrogen glaciers. All of it was learned by an effort that involved thousands of scientists and engineers over decades, operating under the constraints we have been describing. The distances did not stop the science. They shaped it. They imposed timescales that stretched across careers and decades. They demanded patience that is genuinely rare in human endeavor. They required institutions that could maintain commitment not for years, but for generations. And the knowledge that came back through those distances, hours delayed, carefully assembled from compressed data packets crossing billions of miles, is some of the most profound scientific knowledge ever acquired. We know what Titan's atmosphere is made of. We know that Enceladus has a liquid ocean with hydrothermal chemistry. We know that Europa's ocean is larger than all Earth's oceans combined. We know that Neptune has winds faster than anything in the inner solar system. We know all of this because people built spacecraft, launched them into the outer dark, and waited. waited for years of transit, waited for signals that took hours to arrive, committed careers, and in some cases, entire professional lives to a mission that would not complete within a normal human working span. That is what the distances required. And those people paid it. The next generation of outer solar system missions is already beginning. Europa Clipper launched in October 2024. It is currently in transit to Jupiter, due to arrive in 2030. When it gets there, it will execute roughly 50 close flybys of Europa using a suite of 9 instruments to characterize the ice shell, confirm the depth and salinity of the subsurface ocean, and search for signs of material exchange between the ocean and the surface. The radar instrument will look through the ice. Not all the way to the ocean, the ice is too thick for that, but deep enough to map internal structure, identify regions where the ice may be thinner, and reveal the overall architecture of Europa's shell. Everything Europa Clipper learns will set the terms for the debate about whether a lander mission is scientifically justified, technically feasible, and worth the roughly $3 to $4 billion cost of development, plus the 6-year return transit. That debate will be conducted in the late 2020s and early 2030s, based on data the spacecraft is still traveling toward as of this moment. Dragonfly, a rotorcraft lander for Titan, is in development. It would launch in the late 2020s and arrive at Titan around 2034. Its mission is to fly between multiple locations on Titan's surface, studying the organic chemistry of a world where complex carbon-based molecules are accumulating over billions of years in conditions that, in certain ways, resemble the early Earth before life appeared. Not a claim that life is there. A recognition that the chemistry is worth understanding. The Uranus orbiter and probe. The top priority from the 2022 Decadal Survey is in early study phases. A launch in the late 2030s would target arrival around 2050. The mission concept includes an orbiter that would study Uranus's atmosphere, interior, magnetic field, rings, and moons over several years, plus an atmospheric probe that would descend into Uranus's atmosphere, transmitting data on pressure, temperature, and composition during its descent. These missions, taken together, represent the planned frontier of solar system exploration for the next several decades. They are all operating within the physics we have been describing, all subject to the transit times, the communication delays, the launch windows, the funding structures, and the career-length timescales that the distances impose. None of them are shortcuts. All of them are commitments of money, time, and human effort made in full awareness of what the distances require. And each of them was chosen because what they might find is worth what it costs to reach it. That is the decision the planetary science community makes over and over in the face of these numbers. The distances are real. The science is worth it anyway. There is a version of this story that ends with a kind of despair. Distances too great. Time scales too long. Technology too limited. The outer solar system effectively unreachable on any timescale that fits a human life. That version is not wrong as a description of present constraints. But it is wrong as a conclusion. Because the description of what we've learned already from a handful of spacecraft launched across 50 years suggests that the most interesting things about this solar system are distributed throughout its entire volume. The inner solar system, near the Sun, is where the rocky planets are, where Earth is. where human history has played out. But the outer solar system is where most of the mass of the smaller bodies lives, where the ice giants hold clues to planetary formation that the giant planets and rocky planets cannot provide, where the moons of the gas giants Titan, Europa, Enceladus, Ganymede, Callisto are worlds in their own right, with geologies, atmospheres, and, in several cases, probable internal oceans, where the Kuiper Belt holds billions of objects that have barely changed since the solar system formed, preserved in cold storage at the edge of the sun's gravitational reach. The outer solar system is not the fringe of things. It is most of things. And the distances are the price of access, not a reason to stay home. A condition of exploration that the people doing it accept, because the alternative, not knowing, is worse than the transit. The distances are fixed. They are what they are. They impose timescales on missions that no current technology can meaningfully shorten for the most distant destinations. They produce communication gaps that physics cannot close. They demand from institutions and individuals alike a kind of long-horizon commitment that is genuinely difficult to sustain. And yet, spacecraft are in transit. Others are in development. Generations of scientists are planning missions they will not personally see completed. Engineers are building hardware for spacecraft that will spend longer in transit than some of them have been alive. That is the reality of planetary distances, held in its full context. Not just the numbers, not just the physics, but the human response to both. Before we close, there are several things happening right now today, as you watch this, that are worth holding in mind. Voyager 1 is currently about 14 billion miles from Earth. It crossed into interstellar space in 2012. It takes over 21 hours for a signal to reach it one way. It was launched in September 1977. It is 48 years old. It is still functioning, still transmitting, still returning data about the environment in interstellar space, the region beyond the heliosphere, where the sun's solar wind ends and the interstellar medium begins. Its power source, a radioisotope thermoelectric generator running on the heat of decaying plutonium-238, is slowly declining. Sometime in the late 2020s, it will no longer have enough power to operate any instruments. It will continue traveling. It will not stop. At its current speed of about 38,000 miles per hour, it would take about 73,000 years to reach the distance of the nearest star to our Sun. It will not reach that star. It is traveling in the wrong direction. But it is traveling, continuously, launched by the same human civilization that is also building Europa Clipper, designing the Uranus orbiter, sending rovers to Mars, and looking out through the most powerful telescopes ever constructed toward galaxies billions of light years away. The same species that calibrated its senses on the savannah is doing all of that. And Voyager 1, launched before most people alive today were born, is still out there, still going, 21 plus hours from home, returning data about a region of space no human instrument had ever sampled before. This is the same physics we have been describing all along, the same distances, the same light speed delays, the same patient, compounding commitment of time, and the same extraordinary fact that it works. That the spacecraft we build do what they are designed to do, across distances and time scales that strain every intuition we have, because the physics is reliable and the engineering, when it is done right, is reliable too. Now for the full picture, assembled. Mercury. Between 3 months and 7 years to reach, depending on trajectory and gravity assist requirements. A world that swings from 800 degrees on the sunlit side to negative 290 in the dark, with no atmosphere to moderate the transition, a magnetic field at 1% of Earth's strength, and solar radiation streaming across the surface nearly unimpeded. Visited by Messenger in orbit from 2011 to 2015. Currently being visited by Bepi Colombo, arriving 2026. Venus. 4 to 6 months in transit, a surface that destroys our best purpose-built spacecraft in under 2 hours, with 92 atmospheres of pressure, sulfuric acid clouds, and a globally average surface temperature above 860 degrees Fahrenheit. The planet most similar to Earth in physical parameters, and the most lethal surface environment of any planet in the solar system. No human landing is possible with any current or near-term technology. Mars. 7 months each way, over a year of mandatory surface wait between arrival and the return window. 2.5 to 3 years total round trip, with bone mineral density declining throughout, radiation accumulating across the transit toward career limits, a communication gap that reaches 48 minutes round trip at maximum distance, and a surface that requires full pressure suits and life support at all time. The planet most often described as humanity's next step, the closest thing we have in this solar system to a second home, and a round trip that takes 3 years under the most favorable conditions. Jupiter. Approaching 3 years one way, over an hour of round-trip communication delay, radiation belts that deliver lethal doses to unshielded humans within hours, around the most scientifically interesting moons, no solid surface, and a subsurface ocean at Europa larger than all Earth's oceans combined, sealed beneath miles of ice. Saturn. 6 years one way, over 2.5-hour round-trip communication delay, one dedicated orbiter mission in history, spanning 13 years of operation. A moon called Enceladus, with a confirmed global subsurface ocean, active geysers we can fly through, and chemistry matching the conditions that support life on Earth with no approved return mission. Uranus. 9 to 10 years one way, nearly 6-hour round-trip communication delay, visited once in January of 1986 for a matter of hours. Next dedicated mission, not expected to arrive until around 2050, with fundamental questions about internal heat, magnetic field structure, and atmospheric dynamics unanswered for nearly 40 years. Neptune. 12 years, one way, nearly 9-hour round-trip communication delay, visited once in August of 1989 for a matter of days. A planet with the fastest winds in the solar system, a captured retrograde moon with active nitrogen geysers, and no funded return mission within the foreseeable planning horizon. That is our solar system, our immediate neighborhood. The system we were born into, know the most about, and have direct physical access to relative to the rest of the universe. And we have visited most of it once, or not at all. The distance to each planet is worse than you think, not because the numbers are wrong. The numbers are right. 93 million miles to the Sun, 30 to 138 million miles to Mercury, depending on orbital position, 95 million to Venus, on average, 34 million to 250 million to Mars, 365 to 600 million to Jupiter, 746 million to Saturn, 1,600,000,000 to Uranus, 2,400,000,000 to 2,900,000,000 to Neptune. Every one of those numbers is accurate. The numbers are not the problem. The problem is that numbers do not carry with them the rocket equations demand. They don't carry the bone loss, or the radiation dose, or the orbital window that opens once every 26 months. They don't carry the 1-hour communication gap, or the 9-hour communication gap, or what it means for a crew to operate autonomously at that distance. They don't carry the 6-year transit, or the 12-year transit, or the fact that the spacecraft currently heading toward Jupiter's moons will spend 6 years in space before it starts. It's science. They don't carry the 35-year gap between Uranus's only close-up observation and its next planned one. They don't carry the career-length commitments of the people who design and build and operate these missions, or the institutional endurance required to keep them funded across decades of changing political and budgetary landscapes. What you get from the numbers alone is a distance. What you get from the full picture is a condition, a set of physical facts that impose themselves on every attempt to cross those distances, indifferent to our preferences and our timetables and our impatience. Physics does not negotiate. It does not offer extensions. It does not care that a mission was expensive, or that the people working on it have limited time, or that the science waiting at the destination is extraordinary. The distance is the distance. The transit takes what it takes. The signal arrives when it arrives. And the only way forward is through the transit, through the years, through the communication gaps and the biological consequences and the mission cost and the institutional patience and the grief, sometimes, of missions that don't make it. Because what is on the other side of those distances is worth it. We know this not as a hopeful claim. We know it as demonstrated fact. Cassini showed us that Enceladus has an ocean with hydrothermal chemistry. Voyager 2 showed us that Neptune has 1,200-mile-per-hour winds and a captured moon with active nitrogen geysers. Galileo showed us evidence of Europa's subsurface ocean. New Horizons showed us that Pluto has nitrogen glaciers, mountain ranges of water ice, and a haze layer in its atmosphere. Every one of those facts was purchased with years of transit and decades of planning and the careers of thousands of people. Every one of them changed our understanding of what this solar system is. And there are more facts out there. In Europa's ocean, in Enceladus's plumes, in Uranus's interior, in Neptune's atmosphere, in the chemistry of Titan's lake beds, waiting at the end of journeys measured in years and billions of miles, accessible only to the people and institutions willing to pay the price the distances demand. That price is high. It is fixed. It does not get negotiated down. And somehow, despite that, people keep paying it. Because some things are worth traveling for, even across distances that take years to cross, even through communication gaps measured in hours, even across the full sweep of what it means to go, in person or by proxy, to the edges of our solar neighborhood and look at what is actually there. The distance to each planet is worse than you think, and the knowledge waiting at the end of that distance is more extraordinary than you can imagine. That is the solar system. That is where we live, and that is where we are going. Good night.